watch them if you need it.
So guys, if I forget to record something, just remind me to
Yeah,
record that.
please
Please.
record anybody, any person, rather than the Sanam as well by another software if you could. We
Yeah.
need a backup.
Okay, so go through the PDB. So I just because I know the PDB form PDB code for that, I actually find this PDB ID from the article that meant that for the crystal article. That's I know that this crystal article, this PDB form PDB code is actually belongs to my specific protein named HRAS. So I wanted to use that PDB file. I download that and just want to open it. Okay, just let me create. Okay, so let's look at this PDB file. Okay, so all the information you need for the crystal purpose or ND simulation exists in this PDB file. So for example, you see that the name would be, the organism would be Homo sapiens, that yes, we are going to work on a human protein. And this is engineer protein. These have two chain. So first we need to find if, or actually a structure has a missing part or not. Just type miss. So it's good structure, as actually all these is correct. So let's check mutation. So we couldn't see any mutation here. You see, there is no residues that mention that it's mutant. This is just domain. This is called this domain of the HRAS is actually participates in the oncogenic mutation. That's what I already know. So let's check about tag. Okay. So let's go further to see if the files is not unusual files. For example, there is no other in the actually atom name. There is no extra things that we need to care about. So it's okay. So this is the atom part. So guys, be careful that almost all these protein that we are going to work is starting with methionine amino acid or residues. So if, for example, see the residue starts with glycine, just be careful. It's 90% it's a tag. So for the simulation, you need to get rid of tag because it could affect the packing of the protein and interaction of the protein. Okay, so be sure that you undo all these engineer mutation if you had in the PDB file. In this case, it's not a PDB, it's not contain any mutation. And also be careful that you need to delete the tag because it could interfere with your simulation. Okay, in this case, we don't have any tag. And also, let's see how many heteroatom we have. Okay, we have some water. Some of them is a crystal water. Actually, that's important, and we need to keep it for the simulation. And some of them is not important, and we need to delete that. And which water actually is important or not important, you should actually find it from the literature. Okay. And also we have a ligand, GDP, and that's it. So let's this is actually a PDB file that I want to show you to see how a structure could have missing parts. You see, this is missing residue. And if you have a missing residue in the protein structure, this is a section named missing residue. And this is a missing residue. For example, the glycine, the residue number, this is a residue number, and this is a chain, and this is the name of the residue. So the residue, the glycine, that is the 5015 residue number in chain A is missing. So if you want to put this file on the simulation, first you need to fill this residue using homology model, okay? And in the case you have mutation, this is a mutation. This also has a mutation. For example, all this residue, alanine, in this position is actually mutant to that residue. So before starting the simulation, you need to undo this mutation using the Schrödinger. I will show you how to do that, okay? So let's actually open this with Schrödinger. So for actually using the Schrödinger, make sure that you connect it to the global project, okay? So let's open this with Schrödinger. This is a person that we download just from the PDB data bank, okay? So for the simplicity, just go to this part, and before starting, just hit protein. This is abbreviation for the protein ligand software solvents. Sorry, protein ligands and a solvent. And you actually see these ligands in the protein. This is a ligands that belongs to that protein. And this protein is this structure file contain these ligands. So you go through that files. First, we need to change. Before change the visualization step, you see that okay, sorry, let me connect my mouse. Okay, before changing, just look at that. This is a peptide bonds, and this is a residue and of the protein. So you could actually change the visualization step for the protein for the simplicity to the ribbon. This ribbon state and then unshow actually, okay, hide. We hide the structure. So actually this mode, the ribbon bone mode, is actually show the protein base of the secondary structure. For example, the helicases and the beta sheets and the loops. Okay, so let's change the visualization step for the ligands. So that we could go. So from the structure literature study, guys, before starting any simulation, you need to first read the structure article related to your protein very, very carefully, because all the information that you need to care about in your simulation on your preparation step is in the this article that's related to the crystal structure. So I see this, actually I read these so many structure about a structural, actually not experimental, a structural article about the RAS. So I know from the literature that these water molecules, okay, You see, this is a metal ions, just bigger, get that more bigger. Okay. This is a metal ion that's coordinated to actually other residues, the water. So from the article, we know that in the actually in this protein, metal ion is coordinated to 4 crystal water. So we need to care about these 4 crystal water. So for the preparation step, you need to, and let's show the water to, sorry. Guys, if you have accidentally delete something, just Control Z is working in the Schrodinger. So you could use Control Z to undo all the change. So I just want to get together. So this is a water molecule. You see, based off the literature, I see these coordinated to 4 water molecules. This 1, 2, 3, and 4. And also I know that this metal is also coordinated to the ligands, and I see the coordination. And also I know that residue number 17 is also have a coordinator with a metal. You see, this metal should have 6 coordination. So no, it's correct. So if you want to go to have a good simulation, you need to care about all these things. Because if you, for example, treat this residue not correct incorrectly, you lose water coordination, and these could move, and these affect the whole protein. So that's why I mentioned that preparing a structure and treating the structure in a good way, in the correct way, is super important. So yes, this recording. So for the preparing a structure, as I mentioned, that each protein contains the charge residue. That charge residue could act differently in different pH. So we need to know how these charged molecule, charged residue, could be could be treated in body pH. It should be deprotonated or in protonated state. So Schrodinger is super great in treating these kind of things. It's super accurate and super actually easy to use that. For that one, you need to go to the protein preparation step. It just take a while to load. Because it's we are in the Zoom, so it's a bit have a delay to loading the new file. So just let it stay for a while. Okay, good. So the protein preparation has 3 main steps. The first step is that we need to, we want to actually remove the original hydrogen, and actually Schrodinger asked Schrodinger or the Mastro to add hydrogen to the system. And also we need to create zero order bond to the metal. So we need so that we have a correct charge for the metal. And also if we have disulfide bonds between the protein, we ask Schrodinger to create disulfide bonds too. So it's it gets Mastro checking this option, gets Mastro to care about disulfide bonds too. And also in the sum of the protein, the first, because the expression system and engineer something like that, they have selenocysteine, selenothreonine instead of the methionine. So we need to convert that to. And in the PDB file, you see the second PDB file I show you, it contains missing side chain and missing loops, missing residues, okay? So Schrodinger has a program either using Prime to fill this side residue, missing side chain. And also if the number of the residue is short, it's contain a loop, it's not we don't have too many missing residue, we could use that option in the loop, in the loop session, in the loop part. That's ask Schrodinger to fill this missing loop too. And also we need for the starting simulation, we need to add cap termini to each part, to the C terminal and the N terminal of the protein. It's actually so that it could be compatible for the amber. Okay, so we need and you see there is so many. I know that from the literature that these water molecule is important, and I don't care about other water molecules. This is from the crystal. So I ask this program to delete the water molecule that belong to that angstrom for the head group. So just pre-process. And this generating head state is care about the different proteination state of the different residues, charge residues. So this is start. And you see, this is, this is running. It shows that we submit the job and it's running. You could monitor the job if you want to, for example, it's all information and the steps. Okay, so it's done. So to see if our structure having a problem or not, you could view the problem. So we don't have any problem, so we are good. And if your structure have a missing part, too many missing part, missing main atom, main chain atom, or has two different states, I will show you in the next class. It tells us how to deal with that problem. So this is this protein is no issue So then we need to analyze workplace to see what we have. So analyze that. Okay, it's mentioned that we have just a chain named A, and these contain these residues. And also this chain contains a metal ion that you see. And also we have a ligand. Let's see. And this is you see how these actually molecule connect to each other using that one. So in the next step, because the crystal is just a crystal, okay, maybe the protein, because the crystal packing, the structure may contain kind of clash that should be solved using the very short minimization step before entering the MD steps. So if you don't actually, so which end? In 10 minutes, okay. So before actually, so you need to do this first short MD before doing, before entering the main MD steps, so that we be sure that we could create a good topology file, and we be sure that in the we don't have actually no issue in the MD session. So we need to first optimize the structure. This optimized structure create actually care about all these charge residues and charges, care about the charge residues N terminal and C terminal, which is a specific program. So we ask Schrodinger to care about these two, and just do it like that. You see, another job is starting. It's a bit longer than the previous one. Okay, good. It's done. And then we are going to minimize, do the restraint minimization step on the protein. If you check that option, is just minimize or care about the hydrogen atom, but we want to minimize all the system. So just use this force field. This is a force field actually that I tell you, using the actually specific equation to minimize the protein. So just minimize. So any question until that part?
The
Yep.
minimization, the energy minimization that you mentioned, this is simply a geometry optimization, right?
Yeah, exactly. It's help us to relax the structure, okay, and solve so many of the clashes. that
Okay.
exists in the crystal structure, because in the crystal structure, we actually need to pack the system. We have the crystal packing effect, which could affect on the relation between the molecules. So with the structure, with the minimization step, with the short minimization step before starting the MD, it helps to relax the structure and prepare the structure for entering, okay? Solving the clashes, geometrical clashes, yeah?
Yep.
Good.
Thanks.
Okay, it's done.
Oh, hi. I just had a technical question. I was having trouble with my global protect. I was wondering what I should do with that.
Global protector. You have a problem with actually installing the program, or just you couldn't use
Installing it.
uh, mm, actually installing is so simple. Just download the Global Protect on a uWindsor website, and then it's not anything else. Just use
Yeah.
your user pass. So where did you download that file? That's the file.
Oh, I was using my Western credentials because I'm a Western student.
Oh, that's why, because this is our license. It's actually connected you to the University of Windsor, I believe. Actually,
Okay.
I don't know, because I never have a global project for another university that used for another university. I think that's the problem because of that.
Okay, I'll retry and then I'll send an
And
email.
also, maybe what's you so with the global project, you use your username and ID, yeah?
Sorry, you cut out. Can you say that again?
For the username and password, you use yours, yes?
Yes.
So it's this username is belong to Western University, yeah?
Yeah, it belongs to
That's
West.
that's problem. That is the problem. If, for example, for the global protect, if you use my username and password on your system, you could work correctly and without any problem. That's why this is actually with the global protect is actually find you in the Western, and you use the University of Windsor resources and license for our team, actually Tran team that is in your University of Windsor. That's why you couldn't connect.
Right.
Okay, we figure it out. If you couldn't connect, I will give you mine. Okay.
Okay. Thank you so much.
Perfect.
Okay. Take care. Have a nice day.
Okay. So,
I actually have another question.
yeah, sure.
Could we just do a quick recap? I mean, I do remember all the things that you've done to the protein. For example, removing the original H bonds and then letting Schrödinger insert new ones.
Mhm.
But where exactly did you do those settings? I right now don't remember like where to click if I wanted to mimic
Actually,
what you just did.
I just in the first step, I do not doing MD. I just want to prepare a file that I download from the protein data bank. So for the protein data bank, actually after getting the protein, downloading the protein file, structure file from the protein data bank, and Schrödinger has a specific feature that's very powerful to prepare and actually treat these problems that could be exist in the protein files. So we use that actually program of the this program of the Schrödinger is a protein preparation. First, we need to care about the hydrogen. We ask the Schrödinger to delete the hydrogen and add a new hydrogen, and then create a zero bond to the metal. And if you see now, you could see the metal. Let me check that. You see the metal is actually have a charge. You see,
Yeah, yeah.
So before doing that, you see, let me go back. How come this mouse is not working? Do you see any charge?
No, we don't.
So just look at these. This is a water molecule. This is an oxygen. This contain not any actually hydrogen. So now this contain hydrogen and have geometrically correct. You see, this
Yeah.
is clashes. And also, you see, this is a residue named HEAP. You see that?
Yeah.
So this is residue number. Let me check that. Oh my God.